Good afternoon, my name is Connie Jo. Today I'm going to tell you about my paper, Ontology-Based Knowledge Model for Human-Robot Interactive Services. These are my contents. Recently, increasing interest in service robots with artificial intelligence has triggered several studies on developing service robots as human assistants. To perform automated tasks, service robots are not only required to recognize various attributes of the service environment, but they must also determine which tasks and behaviors to perform according to their internal system specifications. To perform human-robot interactive services effectively, service robots should understand user-related knowledge, such as user status information, including user profile, emotional states, and behavioral intentions. They should also understand social concepts, such as organizational structures and human relationships. As with all software, it is not a good option to hard-code everything when solving a problem because it is inflexible. It is impossible to specify the code for every potentiality of what the robot may need to interact with human. Therefore, service robots need to perform tasks in a generalized manner. To perform tasks in such a generalized manner, service robots must abstractly understand the recognition data obtained from the external environment and plan its tasks by combining the data and the existing knowledge. Thus, an abstract and integrated knowledge management of lower-level external recognition data and symbolic-level knowledge is indispensable. This study proposes a knowledge model for an integrated robot framework, which is used to provide human-robot interactive services. Our knowledge model is based on an ontology that contains general knowledge and domain knowledge. The general knowledge provides clear definitions of common concepts, and the domain knowledge provides specific concepts required to understand the information about agents and the environments about human-robot interactive services. The main points of this study are as follows. First, symbolic representation. To maintain the knowledge to be independent of robotic systems, knowledge models need to be represented symbolically. Second, scalability and flexibility. A knowledge model for robotic services must have scalability to be appropriate to represent concepts ranging from class level to instance level. Besides, a knowledge model needs to be flexible enough to generate new information from existing knowledge. As you can see in Figure 1, our knowledge model is composed of 5 submodels. The concepts and the relational properties are designed to cover a wide range of general objects and to maintain scalability and flexibility. Last one is fast knowledge processing. Autonomous robots may need to process a large amount of knowledge in real time. Therefore, fast knowledge processing is necessary. Let me introduce some related works. Galindo et al. Developed a system for automatic map building, which combines a spatial hierarchy of metric and topological maps with a conceptual hierarchy of the semantic properties of places and objects. However, this system lacks expressiveness compared to the knowledge model introduced in this paper. Seo et al. Introduced an ontology-based multi-layer robot knowledge framework. This framework stores low-level visual features in a layered symbolic architecture in simple spaces. However, it lacks the scalability and openness necessary to manage more complex entities and interactions, and it does not contain notions of robot self-models and the user models. Thanos and Bits developed a knowledge processing framework named NoRope. NoRope defines the notion of spatial temporal things and robot self-models. It also introduced computable relationships and describes spatial relations between objects. Our knowledge model shares some concepts with NoRope. However, NoRope's HRI services could be problematic because they lack knowledge descriptions about user-oriented social concepts and relations to provide personalized services that are not computable. The next section is Robot Framework. In this section, there are 3 subsections: the background framework, the knowledge model, and knowledge manager. Before introducing the others, let me give you a quick overview of our background framework. Our background framework is named Artificial Robot Brain Intelligence Framework, in short, RB Framework. As shown in Figure 2, RB Framework consists of Task Planner, Context Reasoner, and our Knowledge Manager. Task Planner executes task planning, goal generation, and controls main flow of the robotic service operations. Context Reasoner performs reasoning based on prologue using dynamically generated recognition information. Knowledge Manager processes knowledge queries from other agents through the interface that controls access to the knowledge model. Knowledge manager uses its existing static knowledge to infer the novel knowledge required by the service situation. More details of knowledge manager will be described in the next sections. Dialog manager is responsible for the conversation with users. Dialog manager identifies the predicate information and analyzes the user intention. This is our knowledge model. To implement knowledge independent of service and system, the system should be directed by abstraction level robot knowledge. Thus, we made intelligent service robot ontology, in short, ISRO. Figure 3 is the overall structure for the main parts of ISRO. It is a generic knowledge model which is not limited to a specific domain. It can be applied to any robot service because it provides a high-level scheme. By considering both low-level information and symbolic knowledge, ISRO achieved integrated management of the knowledge by defining the semantic relation between them. To ensure the scalability and the flexibility of the knowledge, we defined upper-level concepts in 5 main submodels: user, robot, perception, environment, and action. The following sections detail the 5 main submodels. Among the 5 main submodels, first one I'll tell you is user ontology. The knowledge of user is represented in user ontology. Figure 4 depicts the main concepts in the user ontology and their relational properties. These represent social knowledge of the user obtained while interacting with a human. For example, there are emotional state, intention, and age group. Robot ontology defines knowledge about robots as service agents. It includes robot specification and semantic relations with action ontology. Service tasks can be various depending on the capability of the robot. For example, when a robot moves to another floor, the robot must decide whether to use an elevator or stairs, depending on the robot's capability. Thus, to support flexible, capability-driven task planning, our robot ontology defines a representation of a semantic relation between components and capabilities at the instance level, as shown in Figure 5. Perception ontology and environment ontology are discussed together. They interact deeply to define the knowledge of the service environment. The perception ontology performs symbolic mapping for low-level object information perceived in the service environment. It defines various kinds of objects and their attributes that a robot may visually perceive. The knowledge of environment is represented in environment ontology, which is composed of the concepts for places, temporal things, map information, and domain-specific knowledge of the service. For intelligent service robots, it is important to infer spatial associations for providing the appropriate information to the user. Thus, we define hierarchical properties to describe semantic spatial relations. In ISRO, there are 3 map types: metric, topological, and semantic. The low-level metric data from the perception module are translated to topological information and symbolic semantic knowledge. Therefore, the service environment space can be anchored to the abstract space, which the robot can semantically interpret. In particular, the semantic maps express high-level information, including knowledge of relations among objects or among places. The code at the bottom of this page is an example of our description of an instance of a spatial service environment. The action ontology defines events in service situation and the robot actions required to perform service. In our knowledge model, action ontology has various interrelations with other ontology models to define symbol-level actions reflecting contextual information in a service. More specifically, the robot actions range from primitive physical behavior such as grabbing, moving, and speaking, to complex tasks such as guiding and reasoning. In this model, actions are described abstractly that contributing to task planning. When task planner queries an action during a service, knowledge manager returns the appropriate symbolic action for the specific situation using knowledge level inference. This exchange enhances the ability of the task planner to derive the corresponding optimum plan. Action ontology also defines event classes. They are primarily responsible for storing cognitive events that occur during service operations into the knowledge representation. Dynamically recognized external data are stored in the knowledge base in the form of event instances. Moreover, recordable events like medical records can be stored in the same way as cognitive events. Those generated instances are automatically linked to other existing knowledge by abstraction and concretization. The next subsection is knowledge manager. We implemented the knowledge queries and inference functions to utilize our proposed knowledge model. To support flexible extension and management of the knowledge, we implemented a query interface. The query interface has four fundamental functions of knowledge management: create, retrieve, update, and delete. In the knowledge manager, a knowledge inference processor provides relation-based ontological reasoning, path planning, and natural language grounding. Whenever a service robot needs to translocate, path planning is necessary. Our path planning approach differs from existing ones in that it generates paths from the abstracted semantic map information before representing it in the environment ontology. First, the semantic spatial path from the origin to the destination is derived based on architecturally connected to and intersection of between the spaces described in the semantic map. Subsequently, the topological points on the path are connected to generate the final path. If multiple paths are planned, the path with the shortest distance is selected as an optimal path. In this way, an abstract level path planning can utilize the useful situational information, such as the existence of obstacles or the construction status of the path. For a robot to understand what a user said, predicate information extracted from the user utterance must be grounded to the knowledge model. Our knowledge processing module produces a generic symbol grounding approach. The resolution of predicate information has three steps: pronouns replacement, noun resolution, verb resolution. In pronoun replacement step, we have applied word embedding in word resolution. Based on Google Word to Back, the pre-trained word vectors are used to find the words most relevant to each word in the predicate information. To reserve nouns, relevant words that have a high similarity for each of the subject and object words are obtained. Verbs are reserved in the same manner, but by matching to the property namespace. I'll explain the detail later with an example in experimental results section. The next thing I'm going to explain is the results of our experiment. We have validated our knowledge model through a scenario of a robot acting as a medical receptionist in a general hospital. A medical receptionist in a general hospital could meet a diverse range of users. The receptionist should be able to properly handle their complex requests. Thus, the robot needs to utilize a highly scalable knowledge model. The experimental scenario has several steps: encounter, response, understanding, and guidance. Through knowledge inference, the robot would carry out the appropriate greeting action and understand the user utterance and guide the user. Figure 6 shows the whole flow of this experimental scenario. To provide personalized service, it is essential for a human-robot interactive robot to recognize the identification of a user and abstractly understand their personal and contextual information. For this, in the encounter step, lower-level face recognition data are anchored to the knowledge, as shown in Figure 7. A new instance of the recognition event, face recognition, is generated to store this information. To identify the recognized face, a face instance with the same face ID is linked to the face recognition instance. This step involves determining an appropriate symbolic action. In this scenario, the robot responds to the encountered user by giving a greeting appropriate to their age group. In our knowledge model, the class greeting consists of three subclasses: waving hand, bowing casually, and bowing politely. They are ontologically restricted on the target age group property to each age group class: young age, adult age, and old age respectively. The knowledge description for bowing politely is shown in the code you can see now. In this case, since the recognized user is old age, the task planner first receives an abstract action, bowing politely, as a greeting action, and then plans the task corresponding to the action. With the information that the user visited the hospital recently, as a result of the step, the robot politely bowed and said to the user, "Hello, Mr. Kim. Thank you for visiting us again. How can I help you?" In the understanding step, a robot acquires new predicate information from the user utterance and grounds it into the knowledge model. As I mentioned already, the symbol grounding approach for predicate information is conducted during the step. At first, the pronoun I is replaced by the ID of the current user, person 001, which is maintained as the contextual information. The noun flu is then resolved by measuring the similarity between the word vector of flu and other words and phrase vectors. For example, there are influenza, virus, etc. It is hard to determine the exact meaning of the verb get, as it has multiple meanings such as come, bring, do, and earn. To select property candidates, the domain and the range of the properties are each matched to the class corresponding to the replaced subject and one of the object candidates respectively. As shown in Figure 8, the property get disease is reasonably not to be a candidate for influenza, because person is a subclass of agent and influenza is a kind of disease, which are its domain and range, respectively. The robot needs to give the appropriate guide to the user based on the symptom information. This requires the robot to determine the relevant medical department for the corresponding symptom and to guide the user to its location. This code shows an example of information that is used in the process of the knowledge inference. Since influenza is a kind of infectious disease, and infectious disease should be treated by internal medicine department, the robot would guide the user to the internal medicine department. The guidance is based on the path planning process of Knowledge Manager in the way we described it before. This is a video of our study. This video contains the same content as the experiment I just described.
안녕하세요. 또 오셨네요. 조간이 연구원전에 있었던 베타는 좀 괜찮으신가요?
네, 괜찮아졌어요.
앞으로도 건강하시기를 바랄게요. 제가 무엇을 도와드리면 될까요?
독감에 걸렸어요.
많이 아프신가요? 내과로 안내해드릴까요?
네, 안내해주세요.
내과 위치는 3층 제2진료실입니다. 저를 따라오세요.
To validate our knowledge model, an evaluation of the knowledge processing was performed. We measured the execution time for different types of queries and inferences. In this evaluation, we use RDL as the level of knowledge description. The scale of our core ontology ISRO is as follows: more than 1,400 classes, more than 400 object properties, more than 200 data type properties, and more than 100 instances. The evaluation results are shown in Table 1. They were very promising in aspects of variation of query types and speed. In conclusion, the main contribution of our robot knowledge model are as follows. We established a system-independent knowledge model by symbolically and integratively managing all the information from low-level data to high-level knowledge. Scalability and flexibility are supported by providing generic concepts and managing the knowledge model with 5 categorized submodels: user, robot, perception, environment, and action. We implemented the rapid processing of knowledge queries and inference. We experimentally verified the applicability of the knowledge model with some knowledge queries and inferences by measuring the execution time. Thank you for listening my presentation.